Welcome to a new Voltlog. Today we are taking a closer look at this. This is the Pirl charger. It's a 4-port USB charger that will be launched on Kickstarter soon. This unit was sent by the maker free of charge for the purpose of this review. There is a funny story regarding the shipment of this unit. It was first sent by DHL and I received a package that contained some sets of routing bits. It had the correct waybill number, my info on the package, but inside, instead of the charger, there were these sets of routing bits, probably an online order placed by someone else, and I'm not sure how the mix-up happened. Then they sent me another charger via USPS, and this one arrived, so I should have received and reviewed this about 2 months ago. So let's talk about the specs of the unit. It uses an external power supply, 7 to 17 volts DC input. So you have a wide range of options to power it. AC to DC adapters, solar panels, LiPo batteries, car battery. There is a high chance of finding a suitable adapter around your home, but it would have been nice to be able to power it from a laptop power brick. Those are usually 19 to 20 volt output, but I'm thinking they had to put the maximum input at 17 volts because of the DC to DC converter used inside and possibly some power dissipation reasons. You get 4 ports, each capable of 2.7 amps, and we'll put that to a test later. The 4 ports are independent, so a fault on one of the ports is only going to shut down that particular port while the others continue working. It has input reverse polarity protection, thermal protection and ESD protection. It can also detect and optimize the charging current based on the connected device, so I expect to see one of those tiny chips which handles the USB data lines on each port. Another interesting feature they mention on their website is voltage compensation, such that each channel adjusts the output voltage according to the current drawn. If the current increases, the voltage will increase slightly to compensate for the voltage drop that might occur in the cable up to your device. They also have a watt meter on the front of the device showing you how much power your device is pulling from the charger. So let me plug it in so that you can see that. They've also sent me this Meanwell AC to DC power adapter. I believe this is what they're going to be selling with the Pirl charger. We know Meanwell makes good quality adapters, and it just feels heavy, like it really has the required components inside to output this power in a safe manner. So the charger is powered right now, but the display only comes on when there is a load. So I have a device here that will accept the charge. So there you go. There are white LEDs with a 7-segment display. And we also get a LED for each port to indicate that it is active. As soon as I remove the device, the power drops and the display turns off. This will save the power when the device is idle. I like that it has this watt meter, but the way these segments are designed makes for kind of harder reading of the display. It may be the distance between the segments or I don't know, but it just feels like it's hard to read these segments. I think I would have preferred an OLED screen showing the same or maybe more info, because on an OLED screen you can put much more info, but who knows, maybe they plan that for the next version. Also, the watt meter shows overall power, not individual by port, and it has only a 0.1 watts of resolution up to 10 watts and 1 watt of resolution above 10 watts. So it's kind of a rough estimate of what you are using. It's useful in some cases, but not if you want to test a device on the bench and you want to see like things like voltage and current with more accurate results. But let's not forget, this is not a test instrument, so we shouldn't expect that from it. This white indicator for each of the ports can also turn red when there is a fault on that particular port, and I guess we'll put that to a test later. The brightness of the display can be adjusted using this push button. It has 3 levels of intensity and the on-off position. That's a nice feature because the white LEDs could make a lot of light if you keep this in your bedroom, but I noticed that unfortunately it does not remember the setting when you cycle the power, so it goes to full brightness each time you cycle the power. The USB connectors seem to be of good quality. There is that tight fit when you plug a connector, and it has a good grip inside the socket, and that's important because some people will cycle these connectors a lot and they need to be of good quality to handle that. The construction of the device is quite interesting. We have these anodized aluminum panels on the exterior, and then we have FR4 panels sandwiched in the middle. It feels quite robust, and I'm sure it's more robust than all the plastic chargers I've seen so far. It just feels like you could, I don't know, drive over it and it would survive. My unit seems to have a bulge. Let me see if I can get that on camera. Yeah, right there. You can see there is a spacing between those panels. So it seems to have a slight bulge. I think I can even see the PCB inside through that opening. Not sure what to think of that, but we'll take a closer look later when I do the teardown. This is just a prototype, so you would expect issues like this to be resolved in production. Building an enclosure like this is cheaper for small to medium volume, but when you start to have a high volume, I think it would be cheaper to have some kind of injection molded piece in the middle and just keep the outer aluminum panels. For the next part, I would like to test the charger in various conditions. First, I want to try the individual port protection. So, well, this port number 2 is charging a device. I'm going to short port number 3 and see what happens. And we can see the LED turns red, which means this port is disabled right now, but we see there is no problem on port number 2, which continues to charge my device happily. So when the fault is removed, port number 3 goes back to normal operation. So while the short is active through the multimeter, the port is actually outputting some power. I can see around 480 milliamps being pushed through the loads. So yeah, it's not cutting off completely, it's not shutting down the port completely. It just limits the current to this safe value of roughly 500 milliamps. I'm not sure if that's a behavior which is programmed inside the chip taking care of that, but we'll probably see that later when we do the teardown. Let me also show you how the automatic voltage compensation works. So the meter here is measuring the voltage on port 1, and I'm using this load also on port 1, and as I increase the current, we're now at 0.5 amps. As I increase the current, we should see this voltage compensate. You can see the voltage is increasing. So even if we're pulling the maximum allowed of 2.7 amps, we're still getting 5 volts at the end of this cable. So that's a really nice feature. It's not a closed feedback loop, but it is enough for the device at the end of this cable to see 5 volts, which is exactly what it needs and wants. That's a useful feature because USB cables might have a voltage drop, so what you are seeing at the charger output port is not always what you see at the input of your device charging. So this feature compensates for that, allowing you to still have 5 volts at the end of your cable. Next, I would like to check the output noise level, the ripple voltage on the output of a single port. I'm going to use this 2 ohm resistor as a load to load that port with something like 2.4 amps. I'm using a resistor instead of a electronical adjustable load, just to avoid the possibility of the load inducing any noise in the system. So this is just a simple resistor. It will not create any noise in our measurement system. It's in series with this multimeter on amps, just to measure the current that we have. And once I connect that, I will use my oscilloscope probe. I have channel 1 set to AC input with the 20 megahertz bandwidth filter enabled, and I'm using this very short ground connection to avoid picking up any common mode noise. So let's do the measurement. Okay, we're pulling about 2.3 amps for the load, and I'm measuring as close as possible to the output port. And we're seeing about 50 millivolts peak-to-peak noise, and I think that's pretty acceptable for pulling 2.3 amps for that port. That is perfectly acceptable. No device will complain about that level of noise, and I'm sure other cheaper adapters have a much higher noise level. This noise figure will of course be dependent on the AC adapter that you use, because that AC adapter will have its own noise on the output, which will be injected into the Pirl charger. But the Pirl charger mitigates that problem up to a certain level with some internal filtering. I've seen they use some filtering in the product pictures they show on their website. So we'll take a closer look at that later when I do the teardown. But so far it has produced a very acceptable noise level of around 50 millivolts peak to peak. Next, I would like to test the Pirl charger at full load with the supplied AC to DC adapter, the manual one, because that will be the adapter that people would get from Kickstarter, and I would like to test in that setup. I have prepared these 4 electronic loads. I will adjust them to 2.7 amps per load, and I will let them run for maybe half an hour to see how hot it will get, and then we'll take a look with a thermal camera. I want to see if the charger can really output all 4 ports continuously at 2.7 amps and how hot it will get doing that. So let me just start the loads and let them run. Don't mind the values shown on the display of these loads. Some of them are not very accurate, and I'll get back to you in about half an hour. So after about 45 minutes to an hour of running at full load on all 4 ports, the temperature settled at around 75 degrees Celsius in one spot on the back panel, while the front is much cooler. So we can pretty much assume that they're using the back panel in direct contact with the DC to DC switching converters to dissipate the heat. Now 75 degrees Celsius is pretty hot to the touch, so you need to consider this if you're going to run the charger at full power. Ideally, you would want to sit it vertically to allow the air to circulate around the panels to increase the power dissipating capability. If you place this flat on its back on any kind of surface, cooling is going to be worse. The temperature might go even higher. For example, in my test, I had it sitting flat on the bench on my ESD mat, and in this image you can even see the temperature imprint it left on the ESD mat when I moved the charger from that spot it left a very hot area on my ESD mat. So that's why the temperature reached up to 75 degrees Celsius. If I would have had it vertical while running this test, the temperature might have been maybe 5 degrees lower. So it really is important how you're going to sit this charger in the end. I would recommend, if you're going to run it close to its full load or at full load, to maybe keep it on vertical on its side like this. You can maybe even 3D print some kind of mount to keep it vertical. That will increase the cooling capability. The temperature I recorded did not seem to bother the device, and that's to be expected because 75 degrees Celsius is not such a high temperature for semiconductors. Of course, the temperature to junction is going to be a bit higher, but I'm sure it's still within the allowed limits, because I think the DC to DC converters they used inside have a thermal cutoff, so you're safe with respect to temperature. It's going to automatically turn off if the temperature goes above the maximum allowed. Now, realistically, there are very few use cases where this would happen. Normally, the devices you charge will not push this charger to its limits on all 4 ports at the same time, so it will stay much cooler during normal usage. What we learned from this test is that the charger can really output the full rated power continuously, but you need to be careful if you do that, because the back case is gonna get hot. There is only one thing left to do, and that is a teardown of this charger to see how it's built inside. So it looks like we only have these 4 hex screws. So here is the interesting construction method we talked about earlier. Here are the FR4 PCB layers sandwiched together to form this enclosure. Really interesting way of building a product. You can definitely use this method on your own if you're designing something. So let's take a closer look at this board. Starting at the input, we have a nice rugged DC jack. I think this will stand over time quite nicely. I see something in here. It looks like a diode, but it's not a diode, because usually diodes have the cathode marked with a line on the package, but this package does not have any line denoting the cathode. And also diodes usually have some kind of silk screened mark to mark the cathode. So this is probably a TVS diode, a transient voltage suppressor, because it's also marked, it's also connected between the positive and negative. So I think this is here to suppress any voltage transients. Then we have the input polarity protection that is accomplished with a MOSFET, and it's a really elegant solution because you don't waste any power, you don't have any voltage drop on that MOSFET. It has a very low on resistance, and it's a very efficient way of protecting your device for reverse polarity protection. Next we see a shunt resistor. This could be a 100 milliohm shunt resistor, and we have a small chip right here which could be a shunt resistor amplifier. And then on this side we have a tiny 84 microcontroller, which probably reads the voltage amplified by this shunt amplifier, or it could even be a digital output like I2C. So the microcontroller reads that, calculates the power, and displays it on this 7-segment display, which is also controlled by the microcontroller. The microcontroller has its own local voltage regulation. It might be 3.3 or 5 volts. And then we can see the 4 separate banks, each with its own DC to DC converter. So they are indeed individual channels, and you can see they are all identical. There isn't any difference. Power comes in to the DC to DC converter through these small ferrites. So these will help filter out any noise which is coming from the input. Like I mentioned earlier, there will be some noise coming from the wall adapter that you are using, but with the mini-wall power supply they are going to be offering on their Kickstarter page, I think that is well within the accepted limits. But even so, they have these ferrites to block some of that noise. Then a bunch of decoupling caps. This is probably the DC to DC converter with its inductor. The part number for the DC to DC converter is AP65453, and I've checked the datasheet of that converter. It has a maximum input voltage of 18 volts, so that explains the maximum voltage that they will spec for this unit, which is 17 volts. They took a small safety margin. Next to it we have a chip from Texas Instruments, and the part number on that QFN package is TPS 2549. I've also checked the datasheet of that chip. It's a USB charging port controller, and it takes care of the overcurrent protection, the charge current negotiation on the port with the data lines, and also voltage compensation. So that's quite a versatile chip, and it's designed exactly for this kind of product. And also we can see the two LEDs, one is white and one is red. I was told this is a prototype unit which has been hand assembled, but I must say the soldering job is perfect. They must have been using a steel stencil, or not necessarily steel, but a stencil for applying the solder paste on this board, because these solder joints are so even. They have an equal quantity of solder paste, and the parts are really nice placed, even though maybe they have been manually placed. The surface tension of the solder paste, as I've shown in a previous video, which I'll link on screen right now, with soldering SMD parts and methods of soldering SMD parts, the surface tension of the solder paste, while it melts, it will pull these small SMD parts into alignment, which is almost perfect on this board. There's also one thing I wanted to mention. On the top case, we see they have individual light pipes for the LED and for the segments. I was told by the developers of this product that this part is a 3D printed light pipe, and it's used like this in the prototype stage. But in production, they plan to make this part by injection molding, and that should provide a slightly better result for this display. It should be more visible. Let's also take a look at the back of this unit. I'm gonna separate the PCB from the actual aluminum panel. Yep, they are using these thermoconductive silicone pad to transfer the heat from the back of the PCB to the aluminum back panel. And this silicone pad is probably just too thick for this kind of assembly, and it creates that gap in between these plates. That's an easy fix in production. They could use just a slightly thinner silicone pad, and it would still provide adequate heat transfer. We can see the nice gold finish on this PCB, and all of these vias, these are called thermal vias. These are placed right under the components that are going to get hot. So that is the DC to DC converter and its inductor. These are the parts of the circuit that will get hot while running. So they place these thermal vias to pass the heat. Those will a via is actually like a pipe through the PCB material, and it will transfer heat from this side to the back side, and then it will further transfer heat with the help of this silicone pad to the back panel, which is aluminum, and will radiate that heat into the environment. And as shown earlier in my test, we saw this back panel reached 75 degrees Celsius during testing. which means their design actually works. It does transfer heat to the outside and allows the DC to DC converter to operate even at the full load. So they've done a really nice job on this prototype. Top quality assembling quality. I was told this actual prototype was assembled at Macrofab in the United States. They're a company that deals with this kind of prototype building and also large-scale production. And the price of the unit on Kickstarter is going to be about $55. And if you want to get the mean wall adapter as well, and I think they're going to offer a car adapter as well, a car cigarette adapter, that's going to cost you another $25 on Kickstarter. There's been a team of 3 people working and designing this product for the past 1.5 years, and they plan to launch the Kickstarter project in June. What's nice about projects like these on Kickstarter is that they already have the research and development done. The product is fully functional. It has been designed for manufacturing. They just need the funds for large-scale manufacturing, which makes them likely to deliver on time. I think the product will be appreciated by those who are a bit more technical and are searching for a capable USB power supply for powering various systems and devices that require a reliable USB power supply, capable of sourcing higher currents continuously. For example, you could power a Raspberry Pi cluster from the 4 Raspberry Pis or whatever USB powered computer of your choice. You can power them from something like this. I don't think the product will appeal to those looking to charge their phone and tablet bedside, because you can do that with cheaper chargers that are not as high spec as this one. Also, one thing to consider, the Pirl charger does not support the newer charging protocols like quick charge with higher output voltage. So if you need that, this charger is probably not for you. But I'm sure that if their project is a success on Kickstarter, they will develop some newer versions of this product that will have improved functions. So there you go. This was my review of the Pirl charger. You can find the link to their website in the description below. Thank you for watching this video. Let me know what you think in the comments, and I will see you next week.